With the multiplayer-ready gameplay tags component, you can easily manage tags per actor. For example, in this case, each of the 3 colored panels uses its own gameplay tags component and changes color based on active tags through simple tag listeners. In another example, the component drives an entire attribute system, including the character's status and behavior, by reacting to tag changes in real time. This attribute and ability system is part of my MSG course, where I guide you step by step, whether you're a beginner or more advanced, through building a complete game from scratch to finish. You'll find more details in the video description below. Let's get started with building the component. In this episode 2, we'll build the event dispatcher that reacts to gameplay tag changes and create a small debug widget to visualize active tags in real time. We'll continue right where we left off inside the gameplay tags component. Add a new function named update local tag change. This will be used internally, so make it private. To transfer details about tag changes, we need a structured format. Head over to the Data, Structs folder and create a new subfolder called Ability System. Inside, add a new structure and name it s_gameplay_tag_changed_context. This struct is used whenever a tag is added or removed, allowing us to forward detailed context to listeners or other systems that respond to tag changes. It ensures we always know what changed, what the current tag state is, and whether the tag is now active or not. Add 3 variables to this struct. The first one is tag, of type GameplayTag. This represents which tag was changed. Next is active tags, of type GameplayTag_container. This holds the current set of active tags at the moment the change occurred. Finally, add is active of type Boolean. This indicates whether the tag is now active or was just removed. Save the structure and return to the component. In the update local tag changed function, add one input named tag changed context of type s_gameplay_tag_changed. Now let's set up the dispatcher. Add a new event dispatcher to this component and name it on any tag change. This will be fired every time any tag changes. Add an input to this dispatcher named context of type s_gameplay_tag_change, so listeners will know exactly which tag was changed, whether it's active, and what the current state is. Back inside the update local tag changed function, call this dispatcher. Connect the tag changed context input to the dispatcher's context pin. Compile and save everything once. Every time gameplay tags are replicated, we don't automatically know which tag has changed. So we need a function that helps us identify exactly what was added or removed. Add a new function and name it process_tag_diff and notify. This function compares the previous tag container with the current one. It figures out which tags were added, which were removed, and processes each change one by one, so we can notify other systems accordingly. Set this function to private. Now add 2 input pins. The first one is pre-container, of type GameplayTag_container. This input represents the tag state before the update, essentially what tags were previously active. The second one is new container, also of type GameplayTag_container. This holds the new state of the tags, after the change was applied. Together with the previous container, this gives us a clean diff. The first thing we do inside the function is promote the new container to a variable named pre-active tags. We do this right at the beginning, because we want to preserve the latest tag state before any processing starts. This way, if other systems trigger further updates during tag evaluation or replication, we don't accidentally overwrite or lose the accurate reference. By storing this as our new baseline immediately, we make sure the next time this function is called, we can compare against the most recent, already processed state, not against stale or partially updated data. Move pre-active tags to the gameplay tags component category and mark it as private. Next, we want to create a tag change context. Right-click and search for Make s_gameplay tag change context. This will create a new instance of our struct, which we'll use to store detailed information about the current tag change, including which tag was modified, whether it was added or removed, and what the current active state looks like. Connect new container to the active tag's input pin. This gives us a snapshot of the new tag state at the moment this context is being created. Now promote the struct result to a local variable and name it tag changed context. We'll complete and modify this context later, once we know whether we're processing an added or removed tag. If you want, you can hide all unset pins on the make struct node to make the graph a bit cleaner. But in this case, it's often helpful to leave them visible. That way, it's obvious that we're building a new struct, and you can clearly see which values are already being set. Next, we break the new container using the break GameplayTag container node. That gives us direct access to the list of all tags that are currently active, tag by tag, as an array. And what we want now is to go through that list and check which of these tags weren't part of the old container. In other words, which tags were newly added. So we call a for each loop on the result. This gives us the opportunity to compare each tag in the new container individually against the previous state. Inside the loop body, we take the pre-container and call remove GameplayTag on it, and we pass in the current array element as the tag to remove. Now here's the trick behind this setup. If the remove GameplayTag call fails, meaning the tag isn't found in the old container, then we know that tag is new. It didn't exist before, and was added just now. This gives us a clean and elegant way to detect added tags without doing a full diff ourselves, because the remove node already tells us if the tag was present or not. Right after the remove GameplayTag node, call a branch node. Use the result of the remove node as the condition. If the result is false, that means the tag was not found in the previous container, so it's new and was just added. From the false exec pin of the branch, call set members in s_GameplayTag changed context on the local tag changed context variable. Expose only the tag in as active pins. We already set active tags earlier when we first created the struct. Enable the as active checkbox. We check this box to mark that the tag is currently active, it was just added to the container. Then connect the array element to the tag input. This tells the struct which specific tag was affected during this loop. Now, at the end of this block, call the notify local tag changed function. Connect the struct out of the set members node to the tag changed context input. This is the moment where we officially fire the change. With this call, every tag that was newly added gets picked up and pushed through the notification system, so any listeners can react to it instantly, whether it's for gameplay logic, UI updates, or anything else. Now we need to notify the system about all tags that were removed. Right-click and search for break GameplayTag container, and apply it to the pre-container. Then run a for each loop on the resulting tag array. We do this because the pre-container still contains all tags that were active before the update. Any tag that still remains here and wasn't removed in the previous loop must have been deactivated in the latest update. So these tags are no longer part of the current container and can now be broadcasted as removed. Make sure to connect the completed pin of the first for each loop to the exec input of this new loop, so that the newly added tags are fully processed before we begin checking for removals. Now copy the context struct creation and the notify local tag changed node from above, paste them inside this loop and wire them up. Connect the loop body's exec to the make struct node, and use the array element as the tag input. Then, make sure to uncheck the as active checkbox. This clearly marks the tag as removed, which will later be interpreted correctly by all registered listeners. Finally, call notify local tag changed and pass the newly built context as input. This will trigger all tag listeners and inform them that the specific tag has now been deactivated. To finish up, give this function a clear comment that explains its purpose. Right. Compares the previous and current gameplay tag containers and identifies which tags were added or removed. Each change is processed individually by invoking the handle local tag changed function. This allows local tag listeners to react precisely to changes in the active tag set. Then compile and save everything once. Open the update tag state function, because this is where we want to use the new tag diff logic we just created. Start by making a bit of space at the beginning of the graph. Right after the function starts, add a set node for the pre-active tags variable and assign the current active tags to it. This step is important because we want to store the previous tag state before any new changes are applied. That way, we always have a reference to compare against when we evaluate the next update. Next, go down to the completed exec pin of the main for each loop that processes all tags and call the process tag diff and notify function. This function will now handle the entire comparison logic for us. Connect active tags to the new container input and pre-active tags to the previous container input. This connection is essential. We're telling the function, here's the new tag state after updates, and here's what was active before. The system will now check for differences between them. If new tags were added, it will notify them as active. If tags from before are missing in the current set, they'll be recognized as removed. That means from the moment this function runs, we evaluate changes, and every change is then passed on to the local listeners using notify local tag change. This ensures a clean, centralized logic that's easy to maintain and extend later. All of this logic executes either on the server or locally, depending on where the function is called from. Now open the onRep active tags function, because after replication we also need to check for tag changes. This allows us to respond to updates that were triggered by the server. Inside this function, call the process tag diff and notify function. Then connect active tags to the new container input, and pre-active tags to the previous container input. This call ensures that once replicated data arrives, the local side compares the previous tag state with the new one. That way, any added or removed tags are identified and broadcast to the appropriate listeners. Add the following comment to this function. Called on clients when the replicated active tags array is updated. Triggers local tag change processing and notifies all registered listeners by comparing the previous and current gameplay tag state. This completes the dispatcher setup for now. Let's switch back to the map view and continue with the simple debug widget. Navigate to the UI, Common, Widgets, HUD folder. Of course, you can create the widget in any folder that fits your project structure. In this course, I'm placing it here because it's part of the HUD system. Right-click and create a new user interface widget blueprint named WBP_debug ability system. This will serve as our debug overlay and give us a live overview of active tags. Add a canvas panel as the root element. Inside the canvas, add a size box and rename it to active gameplay tags. This box will contain the content for the currently active tags. Then, place a vertical box inside the size box. Rename this one to active gameplay box and make sure the isVariable checkbox is enabled. This is where we'll dynamically list each active tag. Now select the active gameplay tags size box and update its anchor. Hold Shift and Control, then click the center left anchor position. This locks the box to the left side of the screen. Set the position X to 35, the size X to 300, and the size Y to 400. This gives us a clean debug panel with readable width and height. Lastly, shift the position Y to 100 to move it slightly downward and away from the top edge. Now switch over to the graph. Let's clean up the event graph. Delete all nodes except the event construct node, since we won't need the others here. Right-click and get owning player, then call getPlayerState from the BPI_PC_references interface. Just as a quick reminder, in widgets, getOwningPlayer always returns the player controller that owns this widget, so we can safely use it to access further references. In my course, the player controller implements the getPlayerState interface, which returns the player state where the GameplayTags component is added. That's why, in this widget, I'm accessing the component directly through the player controller to retrieve the relevant information. After retrieving the player state, we now need a way to access the GameplayTags component directly. To do that cleanly, switch to the map view, navigate to the Interfaces folder, and add a new interface called BPI_Ability System Provider. This interface will ensure that any actor providing access to an ability system component or related elements can expose that logic consistently. It's an important step for structuring our project cleanly and will be reused in multiple systems to guarantee correct and centralized access to ability-related components. Inside the interface, add a new function named getGameplayTagsComp. Move this function to the BPI Ability System Provider References category. Mark it as const and add an output named GameplayTags comp with the type bpc_GameplayTags as an object reference. This function will act as the bridge to the tag logic across any implementing class. Compile and save the interface, then open bpMyPlayerState. Go to the class settings and add the BPI Ability System Provider interface. Open the newly added interface function and connect the GameplayTags comp variable to the return node. This links our player state directly to its tag component via interface access. Compile and save again, and then head back to our debug widget. Now we can use the MyPlayerState reference and call the getGameplayTags comp function from the interface. This gives us access to the GameplayTag component. From that result, call the AssignOnAnyTagChanged function. This will let us respond to any tag changes from within the component and update our debug view accordingly. Next, drag the active gameplay box variable into the graph and call clearChildren on it. This node removes all previously added entries from the vertical box. We do this at the start of each tag change so we can freshly populate it with the current active tags and avoid duplicates. Now, right-click on the context pin from the event and choose Split Struct Pin. We're not interested in the change tag in this particular case. We just want the full list of currently active tags, which is contained in the active tags property of the struct. Drag off from active tags, call break gameplay tag container, and connect a for each loop to the resulting array of tags. Inside the loop body, create a new widget and select WB_text block. This will allow us to display each tag as a separate text block inside the debug overlay. To retrieve the name of the current tag, drag off from the array element pin and call getTagName. This converts the tag object into its readable name form. Then, pass the result through a toText node and connect that to the text value pin of the text block widget. This way, each tag will be shown as a human-readable string inside our debug panel. Compile and save the widget once. For our HUD, we now need a dedicated text style to ensure better readability. Since we don't have a suitable one yet, we'll create it from scratch. Inside the Style, Text, UI Text folder, right-click and add a new blueprint class. Select the TS-UI text master as the parent class and name it TS_UI_debug_text. Then open it. Set the text size to 12 and change the font color to white. Enable the Uses Drop Shadow option and set the shadow offset to 1 and 2. This gives our debug text a subtle shadow for improved visibility, especially against bright or complex backgrounds. Finally, change the shadow color to pure black and set its alpha to 1 to make sure the shadow remains clearly visible without transparency. Compile and save the asset. Now open the EUI text style enum in the Data, enums, UI folder to register the new style. Add a new enum entry named UI_debug_text and compile and save the enum. This allows us to select the new style within the system using this enum value. Next, open the DA-UI styles data asset in the Data Assets, UI folder. Add a new map entry, use UI debug text as the key, and assign TS-UI debug text as the value. This officially registers the new style in the system. Save the asset and go back to the debug widget. Right-click on the Create Widget node and refresh the node. Now the text style pin will allow you to select our new UI debug text style, and from now on, all text blocks inside the widget will use the correct style with clear and readable formatting. Now drag the active gameplay box into the graph and call addChild to vertical box. Connect it right after the Create Widget node and link the return value to the content pin. This dynamically inserts our new text block into the vertical box so that each active tag is displayed as a separate line. Compile and save the widget once, then return to the map view. Open the WBP_player HUD widget so we can integrate our debug widget into the main HUD. In the palette, search for WBP Debug Ability System and drag it into the canvas panel. Select it, hold Shift and Ctrl, and set the anchors to full screen. This ensures our debug overlay always appears in the correct position regardless of resolution or aspect ratio. Compile and save everything, then switch over to the player state. Right after the authority check, add a delay node with a duration of 1 second. At the moment, all tags are processed and events are triggered before the widget has had time to register to the onAnyTagChanged event. We'll build a more reliable solution for this later, but for now, this delay helps ensure the widget has been initialized before tags are applied. If we press play now, we'll see only tag 2 appearing as active, which is expected. Stop the session, and before removing tag 1, also insert a short delay. Start the game again. Now we see 2 tags being added initially, and 1 second later, tag 1 gets removed. This confirms that everything works correctly. In the next lecture, we'll build the single tag listener. See you there.